Thanks so much for the kind invitation to this very nice conference. So I will talk about the nonlinear heat flow. So it is on our main research is on Finsler manifold. So I will not talk about sub-Riemannian, and I will not talk about the Lorentzian geometry, but Finsler geometry. And this is joint work with Kohei Suzuki. Yeah. Okay, so the aim of this talk is, as I said, develop the theory of nonlinear heat flow. Nonlinear heat flow. Okay, so such a nonlinear heat flow appears naturally in the setting of Finsler geometry. For example, for normal spaces, if we consider a natural heat flow coming from the metric structure of normal space, then it should be nonlinear, and also, as I said, Finsler manifold. And also series spaces, so the curvature dimension conditions. Not a Riemann, just series space. And then this class includes Finsler manifolds, and associated heat flow is nonlinear. Okay, so I want to develop this theory. So there are some achievements recent years, but still much less is known compared with linear case. So I'm very interested in further development of this kind of nonlinear heat flow. And then today's topic is, as I said, as in the title, the Varadhan formula. Or let me first recall the classical Varadhan formula going back to 60s. So it's let me call it point-wise Varadhan formula. It is going back to 60s. Okay. And so this is about the asymptotic behavior of heat candle, and it's like this. So a limit of the T times the logarithm of the heat current PT of xy can be written down by using the distance between x and y. Distance. Okay, so this is very beautiful formula showing the interplay between probability or analysis on the left-hand side and the geometry on the right-hand side. So this formula is known, for example, on Riemannian manifolds. And also sub-Riemannian manifolds. And also actually the spaces. But of course, they are all Riemannian. Riemannian, and Riemannian. Yes. And of course, the existence of heat kernel requires that the heat flow is linear. So on nonlinear heat flow, one can consider kernel. Okay. So on nonlinear case, we cannot formulate like this. So in this case, so nonlinear, so possible formulation for the nonlinear case is the integrated version of this Varadhan formula. Then that integrate form is written like this. Integrate. sorry, okay, integral Varadhan formula. I mean, it denotes this for short by IVF. So this is like this. So again, we consider the asymptotic behavior, p times logarithm of something, and here we integrate. So instead of this heat kernel, so more precisely, we consider the heat flow starting from the characteristic function of some set A. Also here, A, B are some sets. So I will explain the precise setting later. For two sets A, B in your space, we consider the flow acting on the characteristic function of the set B, and we integrate it on the other set A. And what we have at the limit is the distance now between sets can be. So this is the integrated version of the Varadhan formula. And also this is known, for example, on non-smooth setting of non-local on local degree spaces. And so this is the famous work by Hino Ramirez. Three. So yeah, so their work is still on linear case. So this in this case, because of the bilinearity of degree form, we have only linear M group. So this is still linear setting. But this formula itself seems a natural formulation for the also for the nonlinear heat flow. And I will talk about but in this talk I will consider only open sets. Yeah, otherwise we have to modify this distance function, so it's a bit technical. So, and in this talk I think we consider only open sets. And so our main result is that this formula actually holds for Finsler manifolds under some valid assumptions. Okay, so maybe theorem is this integral Varadhan formula holds for Finsler manifolds. Under some assumptions, I will talk about these assumptions later. And of course, the natural question is how about the non-smooth setting of CD spaces? And for CD space, we couldn't show this formula. We could show only the upper bound. So this is much easier than the lower bound. And so this upper bound can be shown also for non-smooth case. Also in the non-smooth case. But for this equality, we could show only in the smooth case of Finsler manifolds. So this is our main result. And so let me first explain what And the setting of Finsler manifold, I think not so many people familiar with this notion. So let me explain what is the Finsler manifold. Finsler manifolds. Okay, so let me mention that in the Finsler case setting, and one important feature is that the distance is not symmetric. It's not symmetric. So the distance from x to y can be different from the distance from y to x. And then in this formula, we have distance from A to B instead of B to A. So this is important feature of the Finsler setting. Okay, so let me record what is Finsler manifold. So we just consider smooth manifold. And then the Finsler structure is a function on the tangent space at tangent bundle, such that it is smooth enough but away from zero. Since if it's smooth also at zero, then it should be Riemannian. So we don't assume smoothness at zero. And we assume homogeneity, but only in the positive direction. So f of CB coincides with C times f of B, but only for positive C. So since we assume this homogeneity only in the positive direction, the distance is not symmetric. Then we also assumed so-called strong convexity for any vector on zero tangent vector. The Hessian of f squared we denoted by Gij using some local coordinate. It's Hessian of f squared in the tangent space. It is positively definite. Positively definite. So this is the convexity condition for f. Okay. Then we can define distance in a natural way using this f. So let me give it. The distance from x to y is of course the infimum of the length of curve from x to y. And as I said, because of the lack of absolute homogeneity, we can include the case the distance is not symmetric. And so this is a natural distance structure. And how about measure? But in the Finsler case, we cannot fix one canonical measure. So there are several choices, but there are several different choices for canonical measures, and I want to choose one of them. So instead, we just fix an arbitrary measure. It just fix a smooth positive measure. Smoothness is not important, I think, but just for simplicity, we usually assume smoothness. And smooth porosity means that in each local coordinate, the density function is smooth sample porosity. Then by using this metric and measure structure, we can consider heat equation. And actually, we can define Laplacian like this. So Laplacian just as the divergence coming from this measure M, and the gradient, this comes from the infrastructure F. And more precisely, this gradient is the Legendre transform with the derivative of F. The derivative is defined just by using the differentiable structure of the manifold, and the Legendre transform comes from the Finsler structure. Just as in convex analysis, this is the Legendre transform. And what is nonlinear is only this Legendre transform. So the derivative is of course linear, and the divergence is also linear, but this Legendre transform is non-linear. And then, okay, Laplacian we define like this. And then we consider heat equation. Now, in this talk, we consider the heat equation like this. So we put one half here, just for, it is just matter of test, but we put one half here. And if we remove one half, then we have different quotient here. So this is the heat equation, and of course, this is non-linear. Non-linear heat equation. Okay. And so we want to consider the integral Varadhan formula. So as I said, the upper bound is very easy, actually. So let me start with upper bound. Upper bound. I estimate. And actually, we can apply a classical technique. I think I'm not so familiar with, but it's sometimes called the Gaffney's method. So it can be applied. And so actually, in the case of upper estimate, we can even obtain a non-asymptotic estimate. I mean, for any open sets, B and not X. Okay, I'm okay. For any open sets with the measure is positive and finite, we can show the following non-asymptotic estimate. For any t, so we define PTAB as the integral there. So this is, so for TT, is the He-Same group coming from the nonlinear heat equation. So it is the He-Same. Yeah, so this is bounded from up by something related to the volume of these sets and the distance. To this. So we have this non-asymptotic estimate for any t. And violating t goes to 0, we can easily show the integral Varadhan formula, I mean the upper bound. This easily implies the upper bound in the integral Varadhan formula. Okay, now I think I have time to explain the sketch of the proof. And this is very simple and actually some kind of standard calculation in GAM calculus. It seems like a standard calculation in GAM calculus. So we put UT with this He-Same group acting on the characteristic function. Is this. Okay. And we consider function f, which is the distance to b, the minimum of the distance from to b and distance from a to b. And what we will need is that minus f is one Lipschitz. Here this distance is 2a, 2b, and f itself is not Lipschitz. I mean, if we consider distance from x or some a, then this is one Lipschitz. But if we consider distance to b, then this f is not one Lipschitz, but minus f is one Lipschitz. Okay. And then also by this definition, one can easily see that in A, f is just distance from A to B, and in B, since this is 0, so it's just 0. But we will use these facts. And then for some Cauchy number alpha, we will choose later. We consider function v of t. It's like this. So if this is function, we will analyze, and at this point, I just remarked that z of 0 is u0 is just the characteristic function of on b, and on b f is 0. So then this is just the volume of b. Okay, then as usually in the gamma calculus, we just differentiate z. Then we use heat equation, integration by part, and so on. We have differential inequality. It's a usual technique. And actually we differentiate. Yeah, and by using the heat equation, ut times Laplacian ut. And since we put 1/2 before Laplacian, we don't have 2. We just have Laplacian. Then we apply integration by parts. Integration by parts. First to t, and next to this. This f. Then we have 2 alpha ut df of gradient ut. So this is just by integration by parts. And so I didn't explain so much about Finsler geometry, but this coincides with the f squared of the gradient ut. And here, alpha and ut are non-negative. And the point is how to control this part. And what we use is that, yeah, so we can control by using the Finsler structure and its dual structure in the cotangent space. But due to the non-reversibility of the Finsler structure, we have to take care about the sign. So, and in this case, we use the relation like this. So minus df of gradient ut is found from above by the dual structure acting on minus df and f of gradient ut. We have minus here, so we try this. And then since minus f is 1 Lipschitz, this is one from above 1. This is bounded. And we continue the calculation. So we have we continue this calculation. Minus f squared gradient t plus 2 alpha ut. And by completing the square, we have nice. Just by completing the square, we have alpha ut. Oh, yeah, this here. And this is nothing but alpha squared to times the yeah. So we have nice differential inequality, and just as usual, this implies E is bounded from above by e to the minus e to alpha squared t times the z. So just by integrating this differential inequality, we have this. And apply this inequality, and we use this inequality to show this frame. Actually, so this PTAB is written by using ut there. Just by ut times the eigenfunction, I don't know, characteristic function of the set A just like this. And then we use just Cauchy-Schwarz inequality to e to alpha f ut, and here e minus alpha f. And characteristic function of A. And so this is the square root of xi. Then I apply this inequality, and to recall that f on A is given by the distance from A to B. And then we have the desired estimate. No, we have the following estimate. Yeah, just by applying this inequality here. And about this part, we use this one. Then we optimize in alpha and complete a proof. And actually, we choose just by calculation to minimize the distance from A to B over T. And we are done. So this is very simple argument. So this is the upper bound, and as I said, this upper bound holds also for non-smooth setting. So let me give a precise setting. We can show this. But holds for say infinitesimally strictly convex so this is necessary to introduce gradient of function. Metric measure space. And we need some additional assumptions such that and the Sobolev space is reflexive. And also local to local Lipschitz, Sobolev-to-Lipschitz property. So these conditions are necessary to connect this kind of Sobolev calculus to the behavior of distance function, but mainly for technicality. So, and these assumptions we can show also in the non-smooth setting, and the calculus we use are mainly developed by Nicola. Calculus. These are okay. So in the Finsler case, this is okay. But also in the non-smooth setting, we can follow this proof. And in that case, the assumption is like this. This is non-smooth. And then next, I talk about the lower bound. I have to erase. And actually, as I said, lower bound is much more complicated. So to be honest, I don't really want to explain lower bound. Okay, and about the lower bound, let me just explain what is the difficulty. I mean, compared with nonsense. The lower bound. And yeah, lower bound is very difficult, much more complicated. And the main difficulty we encountered is the following. Difficulty. The following. So the Laplacian is not symmetric. Yeah, in the non-linear case. So we don't have symmetry. So this was the main difficulty in the proof of the lower bound. And to overcome this difficulty, we use to linearize his same group. Yeah, so this tool was developed in a joint work with Theo in our paper on gradient estimate on Finsler manifolds. But still, this kind of technique is not known in the non-smooth setting, so we can do this only in the Finsler case. And I'm not sure if I can explain about this, but let me briefly explain. So the linearized heat same group is like this. So we consider linearized heat equation. It is written like this. So we have a linearization here, and this is more precisely the divergence of the linearized gradient of the function f, and this linearized gradient is defined by coordinates like this. So, okay, yeah. I didn't precisely explain the notion, but the linearization is done here. So we fix ut. This is a solution to heat equation. I mean, non-linear heat equation. We first fix ut, and by using this ut, we linearize heat equation like this. Then we fix this direction, gradient ut. So this is the linear operator acting on f, and this is linear heat equation. And in this case, we can, for example, show f gradient u. No. So we in this case we have a kind of symmetry like this. So yeah, we have this kind of symmetry. So this linearized Laplacian acting on the function u itself is just the nonlinear Laplacian. And so we can show this symmetry, but here we use linearization. So by using this linearized same group, we can follow complicated calculation in the proof of lower bound, and then we can show the integral Varadhan formula. And let me explain the precise statement of our result. to the main result. And actually, we need to assume some assumptions. So we consider Finsler manifold. Equipped with a measure, and we assume actually for technical reasons we assume that the total mass is finite, and also uniform convexity and smoothness. Then we have the integral Varadhan formula. And here the uniform convexity and smoothness means that uniform convexity means that the Hessian of our Finsler structure has nice uniform convexity and smoothness. And so for more precisely, we can find some C such that this G is coming from the Hessian of the F squared, and then we have this kind of convexity. For any W in the same tangent space, and B is not zero. Okay, this is convexity, and smoothness is similar inequality, but rounded above. So this is smoothness. Yeah, we need these assumptions to construct nonlinear heat nonlinear heat samples. But under these mild assumptions, we can show the integral Varadhan formula. Okay, so this is the end of my talk. And then the remaining problem is that to remove this finite volume assumption and also the non-smooth setting, lower bound in the non-smooth setting. And we have many problems, but all of them are technical, just for technicality, I think. So we hope to have lower bound also in the non-smooth setting. Okay, so I stop here. Thank you very much.